Now let us discuss an example of a satellite. Here we have a satellite of mass m is equal to 2000 kilogram is in an elliptic orbit about the earth. At perigee means the closest approach to the earth. It has an altitude of 1100 kilometer, and at apogee means the farthest distance from the earth, its altitude is 4100 kilometer. What are the satellite's energy E and angular momentum L? How fast is it traveling at perigee and at apogee? This is our question. Okay, let us solve this problem on the following way. Before that, let us understand what the perigee, the orbits, etc. The inner circle is our earth. Earth has a radius r. Okay, the outer one is the counterclockwise direction. The outer one is the orbit of our satellite. Okay, so from the center of earth, this side is close to the earth. Okay, this side is close to the earth and this side is farther from the earth. The closest approach, this is called perigee, and the farthest approach is called apogee. Okay, apogee is the long distance, perigee is the short distance. Okay, so the perigee is 1100. The altitude of perigee is altitude means from the surface of the earth. It is 1100 kilometer away at perigee, and similarly it is 4100 kilometer away at apogee. So this distance is the r plus 1100 kilometer, and this distance is r plus 4100 kilometer. Got it? Okay, so let us calculate mu. Mu is mass of satellite, that is m into me divided by m plus me. M is the mass of satellite, me is the mass of earth. See here in the denominator, small m is, the mass of satellite is very small compared to mass of earth. Therefore m plus me is approximately equal to me. So this me and this me is cancelled. So mu is approximately equal to mass of satellite. Okay, and radius of earth is 6400 kilometer roughly. Okay, so what is r minimum? R minimum is the radius of towards the perigee. Okay, that is 6400 kilometer plus 1100 kilometer, that is 7500 kilometer is r minimum, and r max is 6400 plus 4100, that is 10500 kilometer is r max. And we know a is r minimum plus r maximum. Therefore a is equal to 7500 plus 10500, that is 18000 kilometer, or 1.8 into 10 raised to 7 meter. Say, so we already have a is equal to c by minus e. From that, e is equal to minus c by a. C is gm into mass of earth, but we already know acceleration due to gravity, g is equal to gme by r square. Okay, this is by combining f is equal to ma with g, f is equal to g m1m2 by r square. Okay, from there you will get g is equal to, where a is g, that is mg is equal to g m1 m2 by r square. So that is g is equal to gm by r square. So giving that, So what you can, GME is small g into r square, that is mgre square, where r is the radius of earth. Therefore C is equal to mass of the satellite 2 into 10 raised to 3, that is 2000 kilogram. G is 9.8, R is 6.4 into 10 raised to 6 meter all square. So that you will get 8.02 into 10 raised to 17 joule meter. That is the value of C. Okay, you somehow remember these values for a little bit time, because we are using the same value for one or two examples. Okay, so that is C, the constant. Now E is equal to minus C by A. Therefore substituting the value of C and A, C is 8.02 10 raised to 17, 1 point divided by 1.8 10 raised to 7, you will get minus 4.5 into 10 raised to 10 joule. That is the energy. Okay, so this much energy is required for the orbit to revolve around the earth in an elliptical orbit. Okay, so what will be the initial energy of the satellite before it was launched? So I call it as EI. EI is equal to minus GMME by RE, the initial energy. What is, why it is, initially there is no kinetic energy, only potential energy. That is GMME by RE, that or is equal to minus C by RE. Okay, so that is equal to, so this one 8.02 by into 10 raised to 17 divided by 6.4 into 10 raised to 6. Okay, so you will get minus 12.5 into 10 raised to 10 joule. That is the initial energy. So what should be the energy needed to put the satellite into its orbit? Here we are neglecting all the frictions. So E final minus E initial. Okay, E final we already got minus 4.5 into 10 raised to 10. Then EI is actually minus 12.5. Therefore E minus EI is equal to minus 4.5 into 10 raised to 10 plus 12.5 into 10 raised to 10. That's equal to 8 into 10 raised to 10 joule. Okay, so this much energy is required. 8 into 10 raised to 10 joule of energy is required to place the satellite in the elliptical orbit. Okay, here we have neglected all the friction and all. Okay, that was small quantities. Now we can calculate the angular momentum from eccentricity. So we already got the energy. Now we want to calculate the angular momentum. We can calculate the angular momentum from the eccentricity. So we have R minimum is R0 by 1 plus epsilon, R max is equal to R0 by 1 minus epsilon. Okay, so cross multiplying R minimum into 1 plus epsilon is equal to R0, and R max into 1 minus epsilon is R0. Therefore 1 plus epsilon R minimum is equal to 1 minus epsilon R max, or rearranging epsilon into R minimum plus R max is equal to R max minus R minimum. That is one rearranging, that is only rearranging. Okay, so from that you will get epsilon is equal to R max minus R minimum divided by R max plus R minimum. That's the value of eccentricity. So R max is 10,500 minus 7,000. These are in kilometers. Since it is a ratio, that will go away. So it will be 3,000 by 18,000, that is 1 by 6. Our epsilon is 1 by 6. Okay, it is very close to 0. 1 by 6. So now we can calculate the angular momentum. We have epsilon is square root of 1 plus 2el square by mc square, From that, E square is 1 plus 2EL square by MC square, or L square is equal to epsilon square minus 1 into MC square by 2E. Now we can substitute all the values. Epsilon is 1 by 6, therefore epsilon square is 1 by 6 square minus 1 into M is 2 into 10 raised to 3 into C is 8 into 10 raised to 17 all square divided by 2 into E. E is minus 4.5 into 10 raised to 10. On calculating, you will get 1.38 into 10 raised to 28. Taking the square root, you will have L is equal to 1.17 into 10 raised to 14 kilogram meter square per second. That is the angular momentum. Now we want to calculate the speed at perigee and apogee. We can calculate the speed v of the satellite at any distance r from the energy equation that we learned while we were discussing planetary motion on the earlier classes. So E is equal to, we have two equations, E is equal to half mv square minus c by r. One more is E is equal to half mr dot square plus L square by 2 r square minus c by r. It's two equations. We are taking the first, E is equal to half mv square minus c by r. This is very simple. This is the kinetic energy plus potential energy. So at perigee, we have the perigee radius, this one, this distance, Rp is equal to 6400 plus 1100, that is equal to 7500 kilometer, that is equal to 7.5 into 10 raised to 6 meter. And at apogee, here the farther side apogee, Ra is 6400 plus 4100, that is 10500, that is equal to 10.5 into 10 raised to 6 meter. These are the perigee and apogees. So remember, one point you have to remember at this point, at this juncture, is at perigee and apogee, the velocity have only tangential direction. There is no radial motion. Okay, that's very important. At perigee and apogee, it have only tangential velocities, no radial velocities. Okay. So we can calculate the values. E is equal to, we have the equation E is equal to half mv square minus c by r. From that, V is equal to square root of 2 by m E plus c by r. So let us calculate velocity at perigee. So where you have to replace r by rp, radius at perigee. Square root of 2 by m is 2 into 10 raised to 3 into E is minus 4.5 into 10 raised to 10 plus C is 8 into 10 raised to 17 by R is the perigee 7.5 into 10 raised to 6. On calculating, you will get 7855 meter per second. Similarly, velocity at apogee, here you have to use R as RA. So therefore, square root of 2 by 2 into 10 raised to 3 into minus 4.5 into 10 raised to 10 plus 8 into 10 raised to 17 by RP, RA, that is 10.5 into 10 raised to 6. On calculating, you are getting 5585 meter per second. So the velocity at perigee is higher than that velocity at apogee, that you can. Okay, so I mentioned the point. At apogee and perigee, the velocity is purely tangential. Okay, so you can use the conservation theorem to calculate this. By conservation theorem, angular momentum is constant, that is m, here there r and the velocity are perpendicular, therefore r cross p is equal to rp, that is m vp rp is equal to mva ra both side. From that, va is equal to rp vp divided by ra. So we know the values. So in that way, you are getting 5610 meter per second, almost equal to va as we obtained. That means you can calculate this in another in this way also. All right.